probably everyone's already aware of, but just in case you aren't, there it is. Okay, that's actually number 2. Number 1 is the expert TA. Those who are on trial accounts, the trials will have run up like as of probably yesterday. I called Terry Lair and she said that she has a better plan than what we did last year. Last year what we did is the bookstore purchased the licenses and they said, and if you don't sell them, well, you can keep them. They're yours. You paid us money. We're not giving it back. But this year Terry said a smarter thing to do because of that policy is just if you need one to go to the bookstore, ask for Terry Lair in red there, and then she'll just take you to computer, log in with your expert TA account, and then she will go through paying for it off of the library's account and charge your student bill for the fee. Does everybody understand that part? Right, so you can pay it if you have a credit card, you can pay it yourself just by going into expert TA and following the instructions for paying. But if you want to go on your student bill, go see Terry Lair, and she will have you go through and then pay it off her credit card. Well, not her personal, but the bookstores, and put on your bill. Also, I talked to her about the textbook again, and she hasn't got a price yet on what she can get a printed textbook for, so she doesn't have anything for that. The final announcement is the Loma Linda University School of Dentistry representative will be on campus Monday to talk to students who are interested in dentistry. If you're interested in dentistry and want to meet with her, there are sign-up sheets outside of Darla's office upstairs. So I want to make sure you're all aware of that because we usually have, well, all of the pre-dental students at some time or other have to take this class because it's required for dental school. Okay, please move to the next page. Our first of about 4 clicker questions, which is now open for you to answer. For a 2-dimensional coordinate system, what spatial relationship must the x and y directions have? And it is channel 33, in case people are still having to remember that. Okay, does anybody know how to change the channel on these new type? I thought I knew, but I was apparently wrong. Click channel this one. Well, that's what we thought, but it's not changing channel. Because they don't have a choice. Okay. Yeah, apparently it was proximity. Well, hopefully you can answer now. Okay. So we have, well, I'm sure everyone that's going to answer is answered. We've had 19 answer. And of our 19 that answered, it was unanimous. They must be perpendicular to each other. They need to be such that you can make a unique vector by adding up perpendicular pieces that we call components. Now let's look at steps here for analytical vector addition. Step number 1 is select a convenient set of mutually perpendicular coordinate directions and add them to your figure. Now notice I said select convenient. Some problems it will specify what x and y are. Many times it won't specify and it's up to you. And if you choose, so one vector is parallel to a coordinate axis, it makes life easier. That's why for the Flip Friday thing we did, I instructed you to rotate the picture so that the vector VA was along the x-axis. That just made it a convenient coordinate system so that it was easier to do the work. Then you break each vector into its components using sine and cosine. Now, on the test, you will have the definitions of sine, cosine, and tangent. You'll have the Pythagorean theorem. You don't have to worry about memorizing those. You can look on Moodle right now and it will show you the equation sheet that I used last year, which will probably be pretty similar to what I used this year. I need to make sure that the equations are consistent with what's in the textbook, but it'll probably be pretty similar. So you don't have to memorize sine, cosine, tangent. We're going to use them enough. You should be familiar with them. Add like components. That is, you add the x components together, and separately you add the y components together. As Mrs. Berg taught me way back in Algebra 1, we can't add apples and oranges. So you can't add the x's and y's together. You have to keep them separate when you have them broken into components. Then use the Pythagorean theorem to find the magnitude of the resultant when you have those two components, and use tangent to find the angle. Now, it's easy to have a list like this. Seeing it done is much more useful. Now, we've done it in class once, and you had this problem on Friday. Numbers here are a little bit different, I believe, but I will go through how to do this analytically, and I will keep the coordinate system that's here instead of rotating to choose a more convenient one. So I have vectors VA, VB, and V total. And I want to break them all into their coordinates so I can add the x's together, add the y's together. So I'll start with writing the vectors actually in the magnitude and angle method, just so I don't have to keep looking back up the picture. So I have VA vector, put an arrow over it to indicate it's a vector, is equal to VA, no arrow over that means it's the magnitudes, just how big the number is with its units. And then I need to decide, okay, how much is in the x direction, how much in the y? Right now I'll just say at 22.5 degrees y direction of x direction. How did I get the y of x? A lot of people were asking questions like that. This last one is the reference point I'm measuring from. So I have this angle that goes from the x-axis up to VA. So the second one is that anchor point that I'm measuring from. That's why it says of that axis. The first one is the axis I'm moving toward, and so that's moving toward the y-axis. So that's why it's 22.5 degrees y of x. Similarly, the VB vector has a magnitude of VB, and then I need an angle for it. Now, its angle is the most complicated of the angles here. I know that this is up 22.5 degrees, that's up another 26.5 degrees. And so I know that the angle for V total must be 22.5 degrees plus 26.5 degrees. That one's easy, but that's not my angle for VB. I want an angle that's with respect to the x or y axis. So what I'm going to do to figure out that angle is artificially extend VB, like, right, that last part's not part of VB, but it makes a triangle that will allow me to find what this angle here is. Can't be in the line tool. Now I can find what this angle here is, and if I know that angle, I can also find this angle, which would be the most convenient. So now I have to use my knowledge about geometry. Very simple knowledge. The sum of the interior angles for a triangle is always 180 degrees. So I have a triangle that has V total, VB, and this x-axis piece. And if I add up those angles, I will have this angle here is 22.5 plus 26.5. This angle is 23. So I have 180 degrees equals there's the first angle. There's my second angle, and then this angle here that I put in red that I will call theta. I'll call it theta x. So the sum of my interior angles is equal to 180. Solve that for theta x. And doing some quick math, that's 49 and 23, 72, 180 minus 72 is 98? Or 108? Yes, 108. So I have theta x is equal to 108, and then I'll call this angle here theta b. Supplementary angles make a full 180 degrees, so I'm going to have theta b plus theta x equals 180 degrees, and so theta b is equal to 180 minus 108. Now I've lost all confidence in my ability to do math. That's 80 minus 8. Which is 72 degrees. All right, so I have my angle theta b, and so all that works so I can have the 72 degrees. And since I'm doing this theta b, I'm once again measuring from the x-axis toward the y-axis. And finally, the third V total is equal to, and hey, look, they told me V total is 6.72 meters per second, so I can actually put 6.72 meters per second instead of writing V total there. And then I have at this angle here, which we've already added up to see it's 49 degrees. So there I've written all three of my vectors in the form of magnitude and angle. Why did I write them like that? A couple reasons. Number one is I didn't want to have to keep referring to the picture. I want to have them in a more succinct way of writing. Number two, it's important that we're able to understand how the magnitude and angle system works. Now I'm going to recast these, breaking them into components. So to break them into components, I will draw triangles. So for VA, I'm sorry, it takes me a while to make my pretty pictures that I think are oh so pretty and witty. Okay, I drew my components as dashed lines. And you might say, how did you get those? Well, I had the x direction was horizontal, the y direction was vertical. And in truth, the way I do this is I start at one end and generally just make a nice long line parallel to one axis. And I start at the other end and make a nice long line parallel to the other axis. Well, that worked. And where they intersect, I have my right angle. And so where they intersect, I have this 90-degree angle. And so my components are the pieces that go along those dashed lines starting from the place I started, ending where I ended. So if I put out my components, I can now draw the components on. First component goes like, yeah. Second component goes like, yeah. So notice when you add vectors, you add them tip to tail. If you add the horizontal one and the vertical one, they are going to equal the original vector, the one I started with that I forgot to put an arrow on. So this here has a magnitude of VA. Note that I don't know the value of VA. I don't let that stop me. I say, okay, don't know the value. Let's move on. I know this angle. I wrote it right there, 22.5 degrees. And now I want to find the components. So I have this here is my X component. This here is my Y component. Now in terms of the sides of a triangle, if it's a right triangle, you always have a hypotenuse and an opposite side and an adjacent side. The opposite side is the side opposite to my angle. So here's my angle. Which side is opposite to my angle? Okay, so my opposite is VAY. The hypotenuse is always the longest side. In this case, which one's the longest side? VA. If you can't determine which one is the longest side, it's also always the side opposite the largest angle, which for a right triangle is the side opposite the 90-degree angle. Okay, finally the adjacent side. The adjacent side is the side that with the hypotenuse makes my angle. So clearly VAX is the adjacent. Whoops. So to find VAX and VAY, I look and say, okay, to find VAX, I can use cosine of 22.5 degrees. That's equal to the adjacent side, VAX, divided by the hypotenuse, VA. So clearly VAX is equal to VA cosine of 22.5 degrees. Since I don't know the value of VA, I'm going to go ahead and leave that cosine 22.5 right now. That is longer than writing the number, but I can remember it better. So there's my VAX. To find VAY, that's the opposite side. Sine of the angle is equal to the opposite side, VAY, over the hypotenuse, which means that VAY is equal to VA sine of 22.5 degrees. Taking these two pieces of information, I can now write my VA vector in the form of VA vector is equal to VA cosine of 22.5 degrees in the x direction plus VA sine of 22.5 degrees in the y direction. So now I have once again put my vector here, but now instead of having the magnitude and angle, I have put my vector with the components, the x component and the y component. Now I'll repeat the same thing for VB. I really don't need to redraw my triangle because I used all of my angles y of x. If your angle is measured y of x, you're going to use the same trigonometric function for the same side. If it's x of y, you're going to switch them. So you need to pay attention to the angles. But since all my angles are y of x, they will all have the same form. So I'll have VB is equal to VB cosine of its angle, which we determined was 72 degrees, so there's my VB vector, and my V total vector is going to be equal to, well, we know the V total here. It was given as 6.72 meters per second. Cosine of 49 degrees. Now here, I can calculate the actual numbers for V total, its X component and its Y component. What was the point of this problem? Every time you did it, it was to find the values of VA and VB. So now I can add these up separately, and unfortunately, well, I'm just going to copy this to the next page. I guess you can see what I'm doing. So adding these up, I just add the x's and the y's independently. So I'm going to have, change color. VA cosine of 22.5 degrees plus VB cosine of 72.0 degrees has to equal 6.72 meters per second times cosine of 49.0 degrees. Right, the sum VA plus VB had to equal the total. And going to the y-axis, I have VA sine of 22.5 degrees plus VB sine of 72.0 degrees has to equal 6.72 meters per second times sine of 49 degrees. At this point, you have two equations, the one on the left and the one on the right. How many unknown variables do you have? Two. So two equations, two unknowns. Simple math theory says if you have linear equations equal in number to the number of unknowns, then you can solve. So now you would need to solve for VA, eliminate VB, solve for VA, then put back in and solve for VB. The reason I gave you the hint to rotate your axis was if you rotate the axis, then one of the equations only had one unknown, so you could solve that one instantly, and then put that in the second one and solve it instantly. So that rotation made it easier to break them into components. It also made it easier to do the math and solve for VA and VB. Now I am going to not finish this problem because we probably can all do, solving for two variables with two equations. And go to the other way of solving it. The other way of solving it would have been using the law of sines, which says V total over, let's get to the picture. It's going to come. Oh, yeah, right there. I'm going to actually write it up here. This side divided by this angle right here, sine of that angle. So the sine of this angle, 180 minus 26.5 minus 23, what does that give me? 180 minus 49.5 would be 130.5. Is equal to this side divided by this angle, that's a 23.0 degrees, which is equal to the final side divided by the angle opposite to it, sine of 26.5 degrees. Now this here, yes, question?
Just a quick step backwards. The worksheet that we had, we didn't have that angle 22.5. We didn't have a value for that.
Right.
So at that point,
That doesn't play into the law of sines at all.
No.
Okay.
I was, before we got to the law of sines, I should have asked this a minute ago. But is it possible to solve it analytically the way you did without that angle? Or do you have to rotate at that point?
You could have put in an arbitrary angle and gone through and probably found an answer, but using an arbitrary angle of 0 is a lot easier. Yeah, that's why I put the hint to do it that way. I didn't even try to do it otherwise, because why do it harder than you have to? Okay, so now this one here, I can make any set of equation that is nice for me. So I'll just take the top line, solve that for VA. And that's all I need to do to find the value for VA. That was far shorter than the other work, right? Far shorter. So being able to use different rules appropriately is going to make life a lot easier. And I will very quickly calculate that. 6.72 times sine of 23 degrees over sine of... If it reads my handwriting correctly, which it did not... It thought I had some kind of cosine there. Better. $3.45. Right, so that was quick and easy. Yes, Austin.
Where'd the 130.5 degrees?
Okay, the 130.5 degrees is this angle right here. And so I got that by saying the sum of the interior angles of this triangle is 180. I had not done that before, so I just did it in my head. So you're right, I should have shown you that. So I found, I called this angle theta 3 in our work. So I did it like that.
Okay, got it.
Michael.
Are we going to have to do the long one on the test?
On the test, you will just be told solve this either analytically or graphically. So you'll be making your choices of how to do it analytically. And only this time will you be told you have to solve it graphically. Otherwise, it'll be up to you completely. But I'm going to have, do it graphically so you can show that you know how to do it graphically. Because otherwise, most people wouldn't choose to do it graphically. And I think that brings me to my next clicker question well, we'll see if I'm mistaken. Why are analytical methods preferred to graphical methods for vector problems? Okay, moving on. We had 8 people who said the analytical method is more precise and 11 that said all of the above. This is more of an opinion than a fact question, right? In many cases, the analytical method is easier. In many cases, it's faster, but not in every case. It is always more precise, so I would accept either A or D. I wouldn't put a question like this on a test, obviously, where it's like, well, I think, because you want to have things clear on the test. But I want people to here just think about why it's unlikely people are going to use a graphical solution. Okay, now going to a trajectory problem. So this is the trajectory problem that you had on the Flip Friday class, or assignment. Now I want you to notice the picture I drew there. I didn't draw it, actually, that I took from that Reddit page. That picture is comparing general physics, the red line, to real life, the blue line. What approximation do we make in general physics for our trajectories? There's no air resistance. That we have nothing that's going to affect the ball once it leaves the bat. But in real life, the ball has to go through air, and the air is going to affect its travel. That Reddit page is actually about, well, it starts with, why do people hit the ball farther at Coors Field? Because the air is not as thick, which means that the result is closer to the red line instead of on the blue line. So if you're at sea level, if you're playing at San Francisco or Oakland, you're hitting that blue ball. And if you were playing at Coors Field, you'd probably hit the ball somewhere around here. And that makes a huge difference in the percentage of home runs and fly ball outs. Which is why long ball hitters like to go to Coors Field. Okay, so how do we do this problem? In the Flip Friday, it led you through the steps on how to do a problem like this. A trajectory problem, trajectory is just the name for the path taken by the ball when it's flying in free fall. So the first thing you have to do is break into components. And remember when I said how to break into components, you need to choose a convenient coordinate system. The first rule of convenient coordinate systems needs to be, if you have acceleration, make the acceleration one of your coordinate directions. So once that ball leaves the bat, what is affecting it in our general physics world? Only gravity. In what direction does that point? Down. Now, a big misconception that I've seen people make, my brain goes blank right when I say that. When the ball hits the bat, the ball is having a force put on it by the bat. A force is anything that pushes or pulls. That is, in theory, the topic we're discussing today. And we might get there. I doubt it. A force is anything that pushes or pulls. So when the bat hits the ball, the bat is clearly putting a force on the ball because it's pushing on the ball. Once the ball leaves the bat, is the bat putting a force on the ball? I see a number of people nodding their heads no, and that is the correct answer. The bat force is a contact force. It's only there when they're in contact. But the people who would have said yes to that say, but wait a minute. Why does the ball keep on going? Isn't there a residual effect of the force? The force continues to act? And the answer to that is no. The force was over when the ball left the bat, but the ball had inertia. Inertia is the word for the concept that an object in motion will continue in constant motion unless something makes it change its motion. So that ball would continue going at a constant velocity for all time unless something affected it. And so we just said there's one thing affecting the ball in our general physics world, and that's gravity. And so instead of going in a straight line forever at a constant velocity, it's going to curve and come back down to the earth because of that one force, gravity. It's not a residual effect of the hit. So let's get to doing this. First thing you had to do is to break into components. So when I do these problems, I simply make myself something that is horizontal, which traditionally we call the x-axis, and vertical, which traditionally we call the y-axis. And so I'll have x initial. Where's the ball horizontally when you hit it? Arbitrarily decide. I'm going to hit it from home plate and call home plate 0 for horizontal position. What about the initial height? It was given to you as 0.500 meters. Now I'm going to put under here the finals. The final position horizontally, that's what range means. So that's what we're looking for. That's the ultimate answer we want to find is x final. What about y final? When the ball hits the ground, what will its elevation be? 0. So I knew that one based on the ball hit the ground. So I have my initial positions. Now let's go to the initial velocity. The velocity in the x direction initially. I have the initial velocity is 49.2 meters per second at an angle of 42.5 degrees above horizontal. So I go ahead and draw myself a picture. And this picture is going to have 49.2 degrees. Oops, that's not the right place to write that. It is 49.2. I put the wrong 49.2 meters per second. That's the initial velocity. And I have an angle of 42.5 degrees above horizontal. I'm going to quickly draw in my directions. My y direction, my x direction. Now I'm going to make a nice dashed line here, starting at the bottom parallel to the x direction. That was supposed to be a dashed line. I hit the wrong one. Dashed line. There we go. And then starting at the top and parallel to the y direction. And now I can put in my components, and I'm actually going to do the components freehand. There's my x component. There's my y component. So the x component plus the y component gives me my resultant, the total velocity. And I have given to me the angle of 42.5 degrees above horizontal. So now I shall turn to Alicia. No, Alexis. I've called you Alicia twice, though. It's starting to stick. Alexis, how do I find the horizontal component of this velocity?
Which velocity?
The 49.2 meters per second. The initial velocity.
You said the vertical component?
Horizontal.
Oh, sorry. Isn't that cosine?
It's going to be cosine because I'm relating the adjacent to the hypotenuse. And so we'll do just like she said, 49.2 meters per second, cosine of 42.5 degrees. Can somebody just punch that in the calculator real quick? Okay, give me at least one more. Okay, notice I have 3 significant digits in my problem. I want to go at least 1 digit beyond that, preferably 2. If you're doing it on your calculator, keep all the digits all the time so that I don't lose information through my calculations because I truncated or rounded off. So I kept at least 1 extra significant digit so at the end I don't have too much information lost. So that's my Vx initial. What about Vy initial? How am I going to do that? Okay, that was the vertical component. You see right in that picture. So sine is opposite over hypotenuse, so the vertical over hypotenuse. 49.2 meters per second, sine of 42.5 degrees. And what is that number? 33.23? Okay, so now I have my initial velocities in each component direction. Now we go to the initial acceleration in each component direction. I already changed colors, but okay. What's my acceleration in the x direction? 0. What's my acceleration in the y direction? I heard somebody say it, right? Negative 9.80 meters per second squared. Minus because I had my arrow saying that up was positive, but the acceleration is downward. 9.80 meters per second squared because it's the acceleration of gravity. Remember, I chose my direction as of vertical and horizontal. They weren't given in the problem. I chose them. Why did I choose them? Because I wanted my acceleration to be all in one of the components. So in this case, it's all in the y direction, none in the x. And you might be logically asking, why is that important to me? It's important to me because I'm now going to solve kinematic equation problems. Both of these have the same start at time equals 0, end at an unknown time. Time is what ties the horizontal and vertical motions together. And so I'm going to solve two problems. On the right-hand side, including time, I have all of the variables that appear in the kinematic equations. Which kinematic equation do I use to solve for time if I have that situation? The one that I said is 90% of the time, the one that has all of the variables, the one that is y final equals y initial plus v y initial t plus 1/2 ay t squared. So I'm going to use this equation to find time. So I will put in the 0 for y final to make my life easy. The rest of these are not 0. I'm going to have to use the quadratic equation to find the time. So use the quadratic. Because I'm running out of time, I'm not going to actually find the number. Quadratic. And of course, you're going to get two times. In this case, one will be a negative time and one will be a positive time. The negative time will be the time it would have started on the ground if it had been projected from the ground and then gone up and through the bat at time equals 0. The positive time is the time it goes up in the air and comes back down and hits the ground. So you take those and you say, I didn't even need to know what the negative time was to know that it's not possible for me to have the ball hits the ground before I hit it with the bat. Hence, it's the positive time. But if I'd asked you something else like, it goes over the wall and the wall is at a height of 3 meters, the ball would cross 3 meters twice after it hit the bat. You'd have one time that's a short positive time and one that's a long positive time. In that case, what would the short positive time be? When it's rising and reaches the height of the outfield wall. And then the second one would be when it's dropping and reaches the height of the outfield wall. So you need to think about what those times mean to choose which one you want to use. Once I find the time here, then I bring that over to this side, and I want to find x final. So I'll have x final is equal to x initial plus vx initial t plus 1/2 ax t squared. Well, the ax was 0. The x initial was also 0. And this side becomes trivial once you find the time. So that's how we solve, in every case, a trajectory problem. You break it into the components, and then you solve usually the y direction to find the time, and then use that time in the x direction. Did you have questions? That purely a stretch? Okay. All right. We still have time for at least one more clicker question. What variable ties the vertical and horizontal motion together in a trajectory problem? Okay, that's the same number we've had before. So we have 2, 2, 1, and 14. I asked this question. You can see that it has a reason. Not everyone had the right answer of time. But it's important that you understand the motion horizontal is completely independent of the motion vertical. What ties them together is you have the same ball that's doing both the vertical and the horizontal motion. And so the time for the trajectory is what ties these things together. Now, we have an exam that is next Tuesday afternoon during lab time. You'll have the entire lab time to do the exam. It is closed book. You will have an equation sheet. You should bring your calculator, not your cell phone, not your smartwatch. Apparently some loony PR person at Apple was actually promoting, cheat with your smartwatch until your teacher figures it out. Which seems kind of dumb. So, make sure you bring paper. You'll need to show how you got your answers, and you'll be tested over material from chapters 1 through 3. Question, Ryan?
Is there a restriction on the calculator models?
I actually don't. I trust people not to cheat with the calculator because any good calculator, you can store things in the calculator that could logically be used inappropriately. Okay, so we will, I know I have 1 minute left, but it's a little too small to start talking about forces in Newton's Principia Mathematica, or whatever it's called. It is assumed that review should help. Whether it actually does or not, I guess, is up to, people.
Let me rephrase it. The material on the review is pertinent to the material on the first exam?
Yes. Okay. Do you have questions, Zach?
So, does the review have, what kind of answers you're looking for?
The review will just be reminding us of the things that we've talked about.
Okay, is there, I know you only get 1 point for the answer and then a couple points for, is there a place where you can see, what kind of work you're looking for?
Yeah, if you look at, previous graded exams on Moodle, you'll see exactly how I graded it.